So today we'll be talking about virtual machines. Okay, we'll be getting into what makes a virtual machine, what goes into a virtual machine, and using that knowledge we'll try to characterize a bunch of existing virtual machines. Okay, so through this we'll get a better understanding of a lot of what on a day-to-day basis we might actually be getting exposed to, and the same learnings you can carry on. You can apply to a large number of other VMs that you would come across later in your lives. Okay. All right. Mindset and principles. Something that all of us are already familiar with. Reasoning much more important than facts. Facts can always be looked up, so we don't worry about it. We focus a lot on the method of reasoning. In today's lecture as well, we'll try to use a lot of deductive reasoning to figure out how things should be. Yeah.
The screen is being shared as this, as a mini screen.
How do I fix that? It's your software, not mine. Is everybody seeing like a micro screen instead of a full screen? Let me try sharing it again and let's see if that helps. Okay, so standard method, mindset and principles. All right, we'll focus a lot on questioning. Anything that we see on the screen, instead of absorbing it just as is, we'll try to question why should it be like the way it's actually being described. Okay, so with that, let's get started. There's all of this code that I would be talking about would be available in the repo. Okay, so there's a java.ir.java class file which you can go through. Super simple code. Code is visible to all of you. It just adds two numbers. Okay, what we do is we compile this, and then we look at what that compiled output looks like. Okay, we do that using the java p command. The instructions are there in the repo. You guys can do it yourself. What is it that you see? What are some of the things that you notice? Functions. Okay, so you see that the add function there's an add function here. Similarly, the main function there in the source code. Sorry? Stack. Where do you see stack?
The add function on top of main function.
The add function is on top of the main function. Okay? Okay, fair enough. Let's keep that at the back of our mind right now. What else?
It has code in the
System.
like machine code, like kind of.
Yeah, some kind of machine code, right? Machine code is something, machine code, assembly, all of bytecode, all of those words and phrases we've heard, right? Okay, so just try to, see, and we should be able to figure a few things out.
It is storing the memory somewhere in the code.
Yeah, let's talk about the add function itself, okay? The add function has a and b parameters, so two parameters, and it's actually calculating the sum, right? So what should it map to? What should A map to?
I load 0.
I load 0. Okay. B?
I load 1.
Why do you say so?
Because there are only two parameters.
Only two parameters, two loads, so something, there is no other two here, right? So intuitively we feel that, again, a big reason why I get into some of these very silly descriptions is that very often in practice, in real life, you guys will have to open something up that you have no clue about. Okay? And you have to then apply pure deductive reasoning to try to figure out which part of it is mapping to what, so that I can figure out where is the issue. Okay, so getting into this practice is good, and this one is super simple. Like you guys said, this one is load A. This one is, we'll get into what loading means, but we can feel that there is an A, there's a B here, and we add these two, right? And then we return that number. I is just, should be fairly straightforward, integer. Okay, all right. What else do we see? So that's about the add function. It's pretty much all there is to it. What about the main function? What do you guys see?
First it is
values and then storing them, then loading them.
Yeah, so there seems to be something like a is equal to 10 is happening here, like something like bi push 10, then store 1. Similarly, b is equal to 20, a is equal to 10, b is equal to 20. What else do you see?
something invoking.
Invoking? Yeah.
Static invoking.
So we seem to be calling, and the Java P has actually given us some comment here. So obviously things should be a lot more easily derivable. But in the second half of this lecture, we'll actually go through the bytecode, like binary bytecode, and try to infer things for us. Okay? Okay. What else do you see? Anything else that you see, or shall we move on?
Invoke virtual. Special and invoke.
Invoke, special, invoke, virtual, yeah. And these ones, when we did a system out println, we use a string concatenation operator, right? You guys are familiar with that, right? So the compiler seems to have translated, sort of converted that into a string builder. We are sort of pumping content into that string builder and then using the converted string to actually do a system out println, right? So those are some of the functions here. Anything else that you see? There is a
Something
new
new.
here. Is it the same as Java new? Maybe, maybe not. I don't know. We'll have to figure out. Those are some of the things that.
So maybe
Yes, I think it is instantiating new.
The new string.
Yeah, seems to be instantiating something, right?
String builders maybe.
Yeah, likely string builder, but we'll figure out a lot of those things as we go forward. Okay, so we have some sort of understanding of this. This, what do you call all of this? These sort of instructions? Machine code. Java calls it bytecode, right? But the whole idea is that something that was very legible earlier is suddenly written in the form that feels very different. Okay? Some people differentiate between some people call something like this as assembly, as distinct from machine code being the binary representation of it. I think that's a very artificial separation. It's like saying that 0x11 is different than the number 17, right? They are exactly the same thing, just two different representations, right? So, I'll keep using the word machine code and instructions and assembly in an interchangeable way. That is a bit different than high level source code, because these two are operating at different levels in terms of the primitives with which we are operating, right? The way we are thinking, right? Okay, so let's try to figure out what is machine code. Yeah.
in the previous code, machine code, we had a few numbers missing. What are those numbers representing?
Oh, these.
Yeah.
Oh, good. Good thing that you noticed. Let's say these are from the start of the definition in the class file, where these instructions are stored in some numeric form. The position from that beginning is what these numbers represent. You can see that some of these instructions. So this instruction, bi push 10. JVM spec, can you guys keep it open? Just, you guys have the link, right? So just keep it open, and some of you can also peek into your neighbor's machine. That's perfectly fine. Okay? So just look up bi push. So it would show up in the instruction set reference in the overall spec towards the end. You would find. Anybody has bi push opened up? Yeah. So talk me through how many bytes. It uses 1 byte for the opcode. What is that number? D. So every instruction has an opcode, like a number that, what is that number? Opcode is what? BI push ka opcode is what? Like what is the, show me the BI push, this thing. No. Go to the main, towards the end. Go to 6.5 instructions. Yeah. You would see, yeah, just click on any of them, does not matter. Click on any of them.
0x10.
So BI push
16.
right? 0x10. Okay? And there would be another number, byte, as its operand, right? So 0x10 means the JVM is telling the Java, the class file is telling the JVM that 0x10 BI push is the instruction at this point, okay? And its operand, think about it as argument, is this byte. So we had 1 byte for BI push, 1 byte for its operand. How many total? 2 bytes, which means that the next instruction will start 2 bytes later. So do you understand the missing bytes now? Okay? All right. So most of the instructions in JVM are actually 1 byte long, leaving aside the operand part. Okay? Depending on the operand, it may actually change. So new, for example, you can see that it has 1 byte would be for the new instruction, and most likely it has 2 additional operands. Okay? We'll get into it when we are going deep diving into JVM, all right? Okay, Okay. Let's go ahead for the time being. What is machine code? This is what the hexdump. It's a command that would be available in most Unix machines. So I just did a hexdump. Okay, this is the offset, like position in the class file where this particular entries are. Each row has 16 bytes shown. Okay, so I load 0, 1A. Can anybody quickly verify? I load, it would show up as iload underscore n or something in the JVM spec. All of this is in section 6.5.
Yes, sir.
Just to be sort of clear. Yeah.
Yes, sir. 0x1A.
1A, right?
Yes, sir.
iload 1 is 1B.
Yes, sir.
Okay. I add is 60. Okay. Again, these statements, what I'm talking about right now, all of these are facts. So you don't have to memorize it. So don't focus on whether, I'm just trying to demonstrate to you that physically how these things actually show up on the class file. Okay, that is the more important piece, that each one of these instructions is showing up as is. All right. So similarly to your question, like one of the questions here about where are the missing bytes, you would actually see those arguments show up in the, okay, if you want, like take that as an assignment. Okay. So, and similarly iReturn has an opcode. Okay. How should we think about machine code? Is it that they are binary in nature?
This seems like hexadecimal.
Hexadecimal. Okay. Fair enough. This is a series of hexadecimal bytes. Is this machine code? Yes, no?
No, because you can make hexadecimal to shrink binary code.
Hexadecimal to shrink binary code.
Yeah, to shrink the representation because the binary will take too much. Binary will
Yeah. So you're saying that hexadecimal is just a representation of the set of bits that are there, right? So and that is correct. Like, you know, hexadecimal is ultimately a representation. But just because it looks binary, does that automatically mean that it's machine code? Not all binary is obviously machine code, but is every machine code going to look like binary? Yes, no?
yes, behind yes.
Yes? Okay, we'll see. So this looks binary. This is actually just, if I were to, so this, if you were to translate that, this binary, And if you have to print it, this is what would actually, all right? So just to be clear, matlab, just because something looks binary does not automatically make it machine code. That's obvious. The question remains though, that does every machine code look binary or not? That question remains, okay?
What do we mean by look binary?
Look binary as in, somebody is showing it to you in hexadecimal representation. Ultimately, what are these? These are glyphs, symbols that have some semantic meaning in our mind, right? Seeing a pattern like this immediately tells our mind W, right? Okay, so how something is represented should not really define its meaning for us, all right? Just yesterday in a talk I was posing to a bunch of people. I showed them on screen 0x11, okay, and I was asking people about what do you see, and I got a bunch of answers. The more important thing about any representation is the properties it carries, not the representation in which it has been presented, right? 0x11, for example, the most important property in my mind is the fact that it's prime. 0x11 is number 17, prime. And no matter whether you represent a prime number in hexadecimal, decimal, binary, octal system, primes will continue to carry that unique property of them being prime. Okay, so representation does not matter. What matters is the meaning it actually carries. Okay, so anyhow, we concluded that just because something looks binary does not mean that it's machine code. A lot of times we think about machine code. The moment we think about machine code, what are some of the things that come up? Terse, lower level, right? These are some of the things. Terse is like really short, tiny, small. Okay, so for example, a picture is usually not terse. There's a lot more information so you see a mountain, you see a river flowing and blah, 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 all of that stuff, right? It communicates a lot more information. Terse is like really in the smallest possible way that you can communicate something. Okay, this is my interpretation of terse, just to be clear. I'm not an English expert, but I use this word sometimes to describe machine code. So that's one way to think. A lot of people think about machine code like this. Like when you go through assembly language, why is it that a lot of people are so afraid about machine language? It's hard to understand, right? Yeah, but interestingly, machine code is actually much simpler, just probably 50 to 100 instructions. And they operate at a much simpler level, of layer. Just move something from here to there, add these two numbers, that is all. But it certainly looks terse, right? Why? Because figuring out the semantics from machine language is hard. That's the reason why it actually, feels terse. So it's certainly lower level, but I wanted to introduce a language called Brainfuck. And yes, it sounds funny, and I'm hoping that it just sounds funny and does not sound offensive. If it is sounding offensive, just think about it as a brain fart. Okay, this is a language. Okay, you can think about it as a language. You can think about it as machine code. Okay, and we'll explore some of those things. This particular set of instructions actually prints hello world. Okay, the code is from Wikipedia, but just like I tell you guys never to trust any written word, you've got to verify for yourself. I actually wrote a script to verify. Okay, I call it the Brainfuck VM. Okay, and we will use that as a base. So what I'm going to do is I'm going to stop this screen sharing and let me share my terminal. Okay, is the terminal visible? Should I increase the? Okay. Any bit better? A little more. Now? Okay, and on the screen also this is visible, right?
Yes, sir.
Okay, let me move to lecture 3. Okay. Just to prove it to you that I have not sort of, sometimes in tests what we do is whatever output is expected, we sort of hide it in the program somewhere and just dump it, right? That's okay. So if I were you, this is what I would be wondering. Okay, always approach anybody who's telling you with skeptic, with the mind of a skeptic. Okay, so let me search for. There's no place that I am seeing the word hello. Okay, so what I'll do is, for ease, what I've done is, if I'm passing the argument hello, this is the piece of code that it actually executes. This is the same code, you can verify it later, as you should. This is the same code that I was showing on the slide. Okay, so let's see if it actually ends up doing that. Okay. All right, so this is a VM in action. All right, we had what looked like, machine code, and one second, how do I? Okay, and I need to switch. Okay, screen visible on your, okay, right. All right, so we can think about this as a series of instructions, not too different than the bytecode that we actually saw. Okay, the interesting thing is the number of possible bytes that we see here are much lesser in number, isn't it? In fact, to be precise, it's just 8 bytes. All right, and that is what we want to explore as, like, that's if I directly start with JVM, there's just way too many things that are going to come down your way. Okay, so I decided to use Brainfuck as an approach to demonstrate the main characteristics of a VM, and then we'll get into JVM. Okay, so you would have seen the character, these arrows, right? Greater than, less than sort of thing. What this greater than actually does is increments the data pointer by 1. So the this particular VM has memory somewhere, and the data pointer is pointing. There's something called a data pointer pointing to some place in the memory. Okay, we can increase it to the next point in the memory, the next point, or we can go back and point to some other part of the memory. Okay. So this part is clear. Plus means wherever is the data pointer is pointing to, whatever value is there, incremented by 1. Minus would do the exact opposite thing. Okay, so this one, so the arrows are operating on the data pointer itself. The plus and minus are operating at the value at the data pointer. Clear? Dot means whatever value exists at the current data pointer, output it. Comma means read a value from the external world and store that byte at the current data pointer, wherever the current data pointer is pointing. Okay? All right. Lastly, if an open square bracket means if the value at data pointer is 0, jump to the end of the corresponding closing bracket. Otherwise, continue with the instruction. You can imagine it in your mind as if sort of a construct, right? And similarly, the closing bracket means that if the current value at data pointer is non-zero, then loop back, else continue. Okay, so it's like a looping back sort of a construct, the closing square bracket. This is what we refer to as ISA, instruction set architecture. Okay, this is a word, a lot of times I use the word ISA, and I'll try to use that, I'll try to phrase it as ISA so that it sort of gets really, really driven home for this class. ISA, instruction set architecture. Okay, this explains what the instructions are and what the meaning they carry. That is what instruction set architecture is. Okay, every machine, every computing machine has an ISA. Okay, Brainfuck has 8 instruction ISA. Okay, this is one of the smallest ISAs that you can actually find. All right,
8 instructors there.
There's 8 instruction ISA, yeah. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possible instructions, right? Okay, this is all there is to this particular VM. Okay.
And isn't it just like a programming language? So why call it a VM?
Very good question. Very, very good question actually. I was guessing that I would have to prompt you guys, but good that you guys. This looks textual, isn't it? And if you were to look up on Wikipedia, you would find this being called as the Brainfuck programming language. So it's a programming language. Why am I calling it a VM? Let's get into it. Okay, we'll go through a bunch of slides and tell me if that question ends up being answered after a few slides. If by the break time, if you don't have an answer, please prompt it up. Okay. All right. So what is an ISA? At the most basic level, what do we see? Physical circuits, right? In any computing machinery. Okay, it could be physical circuit of the electronic form, or it could be the mechanical rotating gear kind of thing that actually used to be there in before semiconductors became a thing. Okay, but some physical circuit. Okay, and somewhere way up above is source code, the high level programming language in which we think and we model the world, right? The sort of language that the physical circuits expose, that is one way to think about the ISA, right? That, because ultimately ISA is how we tell hardware to do something. It's the language that the hardware understands. Okay, so it's the instruction. So when we do the add instruction, there's some physical circuit that gets triggered by the bytecode. That number, I add was what? 0x something, probably B0, yeah, whatever. Okay. Whenever that number is received in the instruction stream, the physical circuit of the adder gets triggered. That's one way to think about it. Right? Okay. In practice, and that is a perfectly fine way to think about things. In practice, what we have though is we have the concept of a decoder. In modern CPUs, in very, very early CPUs, the ISA was directly representative of the physical circuits. Okay, but in modern CPUs, you have the concept of a decoder, and the ISA is the language that the decoder understands and translates into what are known as micro ops, micro instructions. This is a word that sometimes you will come across in the future. Okay, ISA, it's still machine language. It looks machine-ish. Okay. There's a physical decoder circuit that actually transforms that language into the underlying circuit with whatever it is. Example, you have Intel CPUs and AMD CPUs. Code compiled for one works on the other, yes or no? Intel CPUs and AMD CPUs. The code that is compiled for the Intel CPUs, does it work on AMD? Depends upon the language. Let's assume that we are writing in C. Let's say you've downloaded the JVM, the Java command itself from the internet. Okay. Do you download separate ones for Intel and AMD, or there is one sort of x86 or x64 that you actually download? Huh? Sorry? Depends.
They are separate
On different architectures also.
Different architectures. Are Intel and AMD different architectures? No. Somebody said no. Some people are saying yes. Argue. Fight. I'm serious. Please argue. Think a little.
EM is a medium, right?
Sorry?
EM is a medium.
Forget about VMs right now. We are talking about ISA, right? Instruction, whatever looks like a machine code.
But the instruction should be same everywhere.
Instruction should be. So if I compile something for, let's say Intel, will it work on a Linux machine that I'm running on an ARM chipset?
If the VM is same.
If the VM, forget about VMs. If I'm compiling it natively.
Natively, it may or may not, depends on the manufacturer, like, however he wants to set the syntax for.
Yes. What is that syntax? That syntax is the ISA. Okay. So every CPU, every processor speaks a certain language. Okay. That language is ISA. How that language gets translated into physical circuitry could be completely different. So, the way it works is people license out ISA. Okay, so AMD, for example, has licensed out the ISA of x86, x64. Okay, the x86 architecture, Intel, 8086 onwards, whatever is the instruction sets, those instructions and the meaning they carry, AMD has licensed out. AMD makes its own physical circuits, which are very different from the physical circuits of Intel. Okay, so the underlying physical circuitry is quite different, but the ISA is the same. That allows a program compiled for one chip to work on the other, so long as their ISA is the same. When you compile something, whenever you compile something, your compiler actually converts your source code into one of the possible available ISAs. Okay, x86 is one, ARM has a different ISA. Okay, ARM is another company that licenses out technology related to chips. Okay. Similarly, there is a open RISC ISA. Java bytecode is an ISA. Python bytecode is a different ISA. Okay. So the machine language that you see, that language is ultimately a language. Just like you can think about English as an ISA for humans, for some kind of humans. Hindi as an ISA for a different set of humans. Okay. If I tell you to do something versus you to do something, the way you guys do it might actually be completely different, but I'm able to still speak the same language to you. You guys understand the concept of ISA now? Okay. All right.
So ISA is defined for a lot of things, like for programming languages too, for CPU too. Is that like that? Like
So you can think about ISA as the programming language for hardware, low enough level. Okay. So at a very high level programming language, very low level programming language, ISA ultimately is the one of the lowest levels that you can think about. Okay.
So there will be many ISAs.
There are many ISAs. I told you. There is the x86, which is for Intel and AMD. The Apple M1 processors actually use something called ARC64, okay, which is essentially an ARM sort of an extension. ARM is yet another ISA. Okay. So if I compile code for Intel and AMD, without some help, I cannot run it natively on a MacBook Pro, which has M1 processor or M2 processor. Okay. Different kinds of processors have different kinds of machine language that they understand. Okay. Every VM, the whole point of VM is that to abstract away this machine language one level further. So the JVM, for example, provides for an ISA. You compile a Java code into a class file for that kind of ISA, and that ISA, how that ISA translates into machine code for Apple versus machine code for Intel, that is done by your Java program. When you run Java,
Yes.
are you guys with me? So you run every class file using the Java command, right?
Yes.
Java command, what it does is it takes this abstract ISA, the JVM bytecode, which is an abstract level ISA, into the underlying processor's native ISA. Okay? So is that something that you guys are understanding?
Yes.
So this is
Every VM has its own abstract ISA.
every VM usually. Sometimes VM will borrow somebody else's ISA. For example, have you guys heard about Ethereum?
Yes.
Right? Ethereum has the concept of a VM, right? EVM. So because it actually has cryptographically enforceable contracts. Contracts are logic, so something gets executed. The ISA that EVM uses is actually something called RISC-V, if I remember correctly. I could be wrong here, but my point is that you can create your own VM using one of the existing ISAs. Perfectly fine. Okay, but often enough, each VM, when you are coming up with a new VM, often enough you would actually build a new ISA.
Why is there some slower that it has to translate again?
Why is it?
Why does it maintain its own abstract ISA?
Portability. Actually, I should have posed that as a question, sorry. The whole idea of VM, when you guys think about VMs, why build VMs? Why have VMs? Why not just write, why should Java not compile into native code on your machine? Why should it have VM, a different ISA than your native machine?
For easier distribution.
Yeah.
Easier distribution, right? Portability?
Yes.
Independent of machine.
Independent?
Of machine.
Independent, that's the same thing, right? So if it is independent of the machine, you can actually deploy it on any machine so long as you have a Java command on that machine which can translate that virtual ISA to a real ISA. Correct?
Yes.
Make sense? So portability is one. What are some of the other reasons?
Security also
Good point. Security.
and the performance. It increases performance.
Yes. And it sounds a little weird. How can something that is getting translated potentially have higher performance?
Almost every code is going to be translated, but it translates using the JIT, Java, not Java, inline, sorry I forgot the name, JIT, it translates the...
JIT, just in time.
Yeah, just in time.
Yeah, just in time compiler. But it is still going to compile to native code only, na?
Yes.
So there's still an overhead. How can it be faster?
It manages memory differently, I guess.
Ultimately, whichever way it manages memory, technically you can always...
Every language is going to translate now. Python is also going to be translated.
Yeah. But think about C. If you write a code in Java, is C always going to be faster than Java? Yes or no?
Most of the times. Depends on how we write the code.
Yes.
Fair enough. There obviously there's good code, there's bad code. Forget about algorithms and stuff for a moment, okay? Because any algorithm that you can write here, you can also write there, right? Purely as a language. You would often come across these fights. This language is faster than that. Is that what things are? Is that how things are?
It's probably about how well it translates to the lower level ISA.
That's a fair point that, things which have almost a 1:1 mapping from from the abstract instruction to the native instruction, you might actually be able to move fast, but that still doesn't work as an explanation about the hypothetical scenario that sometimes your abstract VM is actually faster than the native code. True or not true? We are still investigating it. Let's revisit that in some time, okay? It's, the way your code compilation happens is you've got your source code. Usually there is some kind of an intermediate representation, and then you've got the ISA. Okay. In case of Java, the source code maps to the Java ISA. Okay, the JVM bytecode, which is then translated into the actual machine ISA by the Java command at runtime. Okay. Take, let's say, Rust, for example, or any of the other more normal native languages. There's a compiler called LLVM. It's a framework of compiling technologies. Okay, so when you are, say for example, you wanted to write a new programming language, all that you needed to do was, in case of LLVM, write the front end, which is how to write the source code into the LLVM's intermediate representation. And then after that, so long as you've done that, suddenly your code is compilable across a large number of backends, because LLVM takes care of it. Okay, technically one could think about this as an ISA, LLVM's ISA. Okay, interestingly, DirectX intermediate language. Okay, DirectX you guys remember from the last class, right? So Direct3D's sort of intermediate language has, I'm forgetting, was it LLVM or was it some other? Like it is a subset of one of the existing intermediate representations. You guys will have to look up which one. Okay, so that's to my earlier point that when you're coming up with a new VM, sometimes you can borrow the ISA from somewhere else. Okay, so anyhow, the point that I wanted to communicate was that there's no binary shift from source code to machine code. It's all about levels of abstraction. This is also an abstraction, and for all practical purposes, this can be treated as an ISA. Okay? What happens is that programmability actually goes higher here, goes lower here. Okay? Technically, Intel releases microcode updates. So just to be clear, that's the reason why this arrow is not starting here. This arrow is actually starting a little below this. Most CPU manufacturers have microcode updates, so they patch. So for example, if you have an ISA instruction that says, let's say, mem copy n number of bytes from here to there. Okay. There was a bug that was found, and Intel or AMD could release a microcode update which actually patches this, because that mem copy instruction would get translated into something else. Now this is just as an example. Don't assume that mem copy karke koi instruction hai. All right. But my point is that programmability is much higher here, lesser here, because as you go lower, it becomes physical circuits. You cannot sort of change them. Semantics, much higher here, lower here, correct? Semantics, do you understand? It's the meaning of something. Okay? When you go through a Java code, going through it, you understand a lot more than if you were to be going through a bunch of assembly instructions, isn't it? Right? You're dealing with a higher level of abstraction. That is what makes a language higher level language, right? Okay, so you can deal with higher level primitives. You don't have to think about how data is moving here and there, etc. Okay, so that is what actually I mean by semantics are higher there, lower. Yeah.
So the time might be like lesser in the native code because of this abstraction. So such that to lose like maybe on compiling to a lower level language or ISA, instructions might get a little bit weird. So the translation might not be correct. To fix those translations, the compiler might add some more code as well.
Yeah, that is usually true. That is true. So which is what I mean by, good that you sort of preempt. Hardware level optimizability, like how close you are running to the most optimal side of things, usually gets better here, because usually your compiler is doing the job for you, but somebody who can really hand tune stuff, they can do things actually a lot better, which is why in a lot of older code there would usually be a lot of hand coded assembly. But as compiler technologies have improved significantly, we rely less on this, because the advantage of the semantics much more, plays out a lot more strongly than the disadvantage of being able to optimize every single instruction. Understood? So which is why we usually program it at this level. Make sense?
Yes.
Okay.
Decoder is like Java followed by the bytecode.
Sorry?
Decoder in here, it's like Java followed by the bytecode.
So this, I'm giving the example of a real machine, but the same concept can be applied to the to the Java VM as well. Okay. In case of the Java VM, what is happening is, you can imagine this side, the physical circuit, as your actual processor. Okay. This is the bytecode. This is the actual processor. This is Java. What it is doing is, it is taking the Java bytecodes, because that's the ISA it exposes out, and it is mapping each one of those into some lower level, actual underlying processor's bytecode. Okay, so yes, Java can be thought of as the decoder, logically speaking, that maps the Java ISA, the Java ISA, to the actual underlying Intel or ARM or any of these other processors. Make sense? Okay. One of the things here is distance of optimization is much higher here. What do I mean by that? Imagine you were sitting at the decoder. You are the decoder. You are sitting there. You are seeing a bunch of instructions come your way, right? For you to figure out, okay, you know what? In this series of instructions, this probably I can eliminate. It's not really useful. It's not doing anything. An example would be a is equal to 10, and then immediately after that a is equal to 20. A is equal to 10 is useless, so I can eliminate it, right? So those sort of simple optimizations are possible at the decoder level, but you can't really, the distance to which you can look to figure out the optimization patterns is much lesser when you are here, right? Imagine that. Are you able to get a feel for why that would be the case? Whereas in the case of source code, you can actually have, the compiler can actually have a view of the whole program in one go, right? Why? Because compiler is usually working at a compile time, whereas this guy is running at a runtime. Okay, so much higher distance comes at the cost of much more time, right? Runtime cannot afford to be slow, so it can do only usually micro optimizations. Okay, so that's what I mean by the distance of optimization. Question is, how do we know an ISA is exhaustive? ISA to ban gaya. We created a bunch of, so in case of Brainfuck we had those 8 instructions, right? If somebody tells you you can write any logic in it, how do you know that person is speaking the truth? Imagine you were a processor manufacturer. You created an ISA for yourself and you put it out. Okay, somebody realizes 1 year down the line, to implement this kind of logic that I have in mind, I needed this particular instruction, but it's not there. Disaster, isn't it? So whenever you think about an ISA, be it for the VM or be it for the actual underlying processor, you need to make sure that that ISA can express any kind of logic that you can imagine, isn't it? Yes, no?
Modify the existing.
Sorry? Sorry?
We can't modify the existing ISA to add our own features.
Of course you can add and remove, okay? But imagine the cost of it, okay? Let's consider both the scenarios, VMs and actual processors. Actual processor, in case of actual processors, you sold n number of processors, right? The processor has a layer which is the ISA that is fixed, okay? You cannot actually, the cost of changing it is actually much more tricky. In case of virtual machines, you've actually gone ahead and pushed something. Anytime you change the ISA, add or remove something, every single compiler that had been compiling for that ISA will need to become aware about it, isn't it? Imagine the number of people who've been using compilers. How many times do you update your compiler? Right? So as an ISA designer, be it for the VM or be it for the actual processor, you need to make sure that you are bloody exhaustive. Correct? You cannot afford to discover later that there is some logic that is not possible to be implemented in this instruction set architecture. Right?
But we can't always be exhaustive.
You can't always be exhaustive.
Yeah, it might be the case that we might need to add some features later on.
Yes.
So how can we cover that?
Which is where the theory of computation comes into picture, which is what we'll talk about now. Okay? But we are a little ahead of, we are behind time right now. So I'm going to take a break earlier than later, than planned, and we'll converge in 10 minutes from now. Okay? Because this is super important. Usually gets presented in the most boring fashion to people. But the applicability of this is so humongous, I want your full attention, which is why we'll take a break now and we'll resume in 10 minutes. Okay? So this is the core essence of computation. Okay, there's a lot of discussion we were having just now during the break about, is a language a VM? Okay, or does it get compiled into a VM? All right, so a lot of those abstract philosophical questions we were having, and all of that boils down to the essence of what it means to say that we are computing something. Okay, so I need each and every one of you to be fully engaged inside your brain when we are discussing this. There's a lot of thinking I would be demanding from you on this slide. Okay, this is a slide where I'll be demanding the most amount of mind share. After that, things become easy. So, sort of pay very close attention. What we'll try to do is try to define what computation is. Okay? Any thoughts before we get started? Any ideas about how should we define computation?
Converting the machine code to the bytecode.
Machine code to the bytecode. Contextual answer, I would say, because we are talking about machines and all of those things right now. It's just your definition is colored by that lens. I want all of you to sort of dig a little deeper and try to come up with some sense. Again, there's no point about thinking right or wrong, and that's not what we are trying to do here. We're trying to articulate what all of us intuitively feel about computation. Yeah.
So we have some input.
Yeah.
We want to convert it to some output.
Okay, so some black box that for some mapping of inputs has some mapping of outputs. Okay, we refer to this as a functional definition of computing. Okay, what else? Yeah, sorry.
The minimum set of logics in which we can implement anything.
Interesting. So the minimum set of logical constructs with which we can implement any kind of, okay, fair enough. Calculations, okay. Calculation versus function versus what that guy there talked about, the logical constructs. Are all of them equivalent, or is there some difference? Is there more to logic and function than just calculation? Yes, no?
Yes.
Okay. No? Depends upon how we define the word calculation ultimately, right? But fair enough. Let's try to, what I'm going to do is, I'm going to give all of you some resource, and you'll soon understand what I mean by that. Some resource. You guys need to think what kinds of potential logic you can build on using that resource, and what kinds of things you just cannot build for each one of them, okay? All right, first one. There is absolutely no state available to you, no concept of memory. And just to make things easy, I'm going to start off, the easiest one is going to be, I'll do that, I'll not ask you guys, okay? Only the difficult ones for you. No state. An example would be a linear circuit, for example, an adder circuit. The moment I put something in as input, say for example 2 numbers, imagine a physical circuit, 2 numbers, the sum actually comes out. The circuitry does not require any memory per se. There's no memory. It's pure logic transistor switching, pure logic gates, right? Zero state. Okay. We often refer to this as combinational logic. Yeah, full adder, half adder, all of that stuff. Okay. So this is zero state logic, which is what we often refer to as calculation. Not all calculations fit this bucket, just to be clear, but zero state for now, okay? Then I'm going to give you finite states. Remember, finite state, not finite memory. So it's not like I'm giving you memory. I'm just saying you call out some n number of states, and then you articulate your logic in the form of moving from that state to this state to some other state, or coming back, whatever. What kinds of logic you can build on that? With this, let's say I've given you 2 possible states. What kind of logic? You can associate any meaning to these 2 states. Ah, good. I'm glad that at least you guys are thinking if else, right? What else? Huh? Switch case, good. For while. Good point. Can I write for while in a any of these loops in a way which does not terminate? So then technically is the number of states that my logic is in can potentially be infinite, correct? On the other hand, if I were to use for each, right, going by the looping wala example, for each, the looping construct has a very well defined state. Would you agree? For each versus a generic for loop, because generic for loop I can always decrement the counter itself and just do infinite possible variety, infinite combinations of logic, right? Do you understand the difference between for each versus a generic for loop?
Yes.
Okay. So we got if else, we got switch, we got loops, and I'm just specifically classifying the for each kind of loop. The whole point is finite state. Finite state, as in the way I'm representing the logic in my mind, I should be able to imagine my program jumping from this state to that state to that state to that state to that state. Make sense? Okay. So, good. I you guys are making progress. This is what is called as finite state machines. I'm going to, sorry, go ahead.
So it can also be given an index, getting a position in array of a memory.
Given an index. So long as all the possible values that your index can have is predefinable, then yes. Remember, you are representing you need to be thinking about it in terms of not memory, but the state that your logic, your program as a logic is moving around in. Okay, so usually we'll not classify that as a finite state machine because the values can vary to whatever level. Okay.
Everything in no state?
Sorry?
Everything in no state?
Everything in no state will naturally fall here. So I think that is not under question. Next, I give you a stack. Some area where you can push. Stack you guys are familiar with?
Yes, sir.
You can push and you can pop. Beyond all the kinds of logic that we thought about, what additionally can do you now become capable of expressing? Remember, this is not memory. This is stack. Undo. Undo as a logical construct. Fair? Yeah. To some degree, it's there. Yeah. Scopes. Define that a little better.
Like variables have scopes.
Variables have scopes.
We can store like in a hierarchy.
Okay, so because there is nesting involved, right? A variable defined in this function that then calls that function, and that function has its own set of variables. Because there's some sort of nesting involved, so long as the lifetime of that variable was within the scope of that function definition, because we are calling different functions, the lifetime of those variables is directly linked with the lifetime of that nesting. So it can be seen as stack. This guy calls this guy, so all existing stuff is pushed. Now I'm dealing with this logic. This guy calls that guy, further thing is pushed.
Evaluating the mathematical expression.
Yes. Evaluating a mathematical expression can be seen as like prefix notation and those sort of things. What else? Think a little sort of.
First slide you showed us all the commands were written in stack only.
Were written in stack. What do you mean?
Where you showed us some two functions of Java and the bytecode.
That was stack. Yes, that was stack.
That can be example of computation.
Yes, that kind of computation. But what we are really trying to figure out is what kinds of logic is possible. You are right that the nature of those bytecodes seem to have a stack angle to it, and we'll soon get into the way that stack is useful in JVM. But right now we are talking in abstract. We are talking about the concepts of logic. Okay? So when you have stack available, just like the moment we had finite state available, you were suddenly able to implement if else. There's no way you could have implemented if else in the zero state scenario. Right? Sorry.
Running a program, like running a Java code.
Running a Java code. Is all kinds of Java code possible just with stack alone?
No.
Recursion. Recursion?
We can do it with stack.
Think. Is recursion possible with stack? Yes, no?
Yes.
So then your argument about recursion being an example of what is not possible on stack, it becomes invalid. Yeah.
Since we can have recursion in stack, that means we do not need to be in a finite state anymore.
Yes. So which is why it is capturing more space. Right? Each one of these is actually getting into more and more spaces of logic. Right? With stack, recursion somebody called out. Okay, so recursion is one. Function call we discussed at the beginning. Right? The moment you are calling a function from an existing sort of logical flow, you called a function. All existing states that you had captured will need to be pushed somewhere, so that space becomes available for the next function that you've called, correct? Yeah.
Can we have a multi-level stack, like stack inside a stack?
Yes, you
When
can.
we call a stack,
So-
we call a function, we make another stack inside a stack that will have the variables.
Yes, but the defining property of stack as against memory is that you can always access only the top of the stack. You can only pop. Say for example, just because you have a stack 3 levels below in a stack, you have a substack embedded in that. Without popping uske upar ki layers, you cannot access this stack. So long as we understand it, yes, this happens all the time. We'll see this in the JVM also.
Since we have access to recursion and we do not need to be in a finite state, that means we can implement while, for and other kind of loops.
Think.
That's stack infinite state.
I just not talked about that. In stack, the defining property is once you have pushed something, anything below the top of the stack, if you want to access it, the only way to access it is pop. And the moment you pop, those data points are gone. You cannot push something back, you cannot pop it, let me access this and then push these again. Okay. So what about loops which are accessing an array? Is that possible on a stack? You cannot, because you cannot access something that is actually much more deeply embedded. Is that making sense? Okay. All right. So let's see what stack enables us. Function calls, recursion, at least some of these things, might be a bunch of other things. I want to leave you guys largely with a strong sense of intuition about these things. This is what is known as push down automaton. Okay. I'm throwing these words in here because theory of computation for a lot of people is actually one of the most boring topics because it's in the abstract. Okay. But these are very, very genuinely useful and practical things. It is this using which we'll try to assess if Brainfuck can implement any and every kind of logic or not. This is the only way we can actually figure things out. All right. Next, I give you addressable memory. Now your things become arrays, any kind of for loop, because you can access any memory at any point in time. What kind of logic can you guys imagine that is not possible in this? So you have all of these things and addressable memory.
A bunch of algorithms.
Which algorithms is not possible now?
So we still can't use the for loop and while loop.
Why? I've given you addressable memory and any amount of addressable memory that you want. It's finite, but whatever you want, 100 terabytes of memory, I'll give you 100 terabytes of memory.
Now use a bunch of algorithms.
Yeah, you can use pretty much. So the assertion that I'm making is that, without getting to mathematical proof of it, is that you can implement any kind of logic. The only way you can counter it is by coming up with some kind of logic that is not possible. And there are some kinds of logic, yes, which are not possible on such a machine. Okay? But vast majority of what we consider as computation will actually fall under this bucket. And this is what is called as a Turing machine. Just yesterday I was speaking to a bunch of engineers where I was talking about that 0x11 thing. And I showed them the Brainfuck language and I asked whether you can build any logic on this or not. And there was at least one guy who was able to say, there's something about memory which tells me that this is Turing machine. Like some patterns were firing in this guy's mind because at some point in time he would have had a conversation like this in college. Okay? The point is, what defines a Turing machine is fully addressable memory. All right? Okay? So now let's move forward. There's a thing about Chomsky's hierarchy about what kinds of languages sort of map to some of these levels of computation. I'm not going to get into it. It's only going to be overburdening you. So the question is Brainfuck a Turing machine? Let's look at our favorite VM again. Where is the addressable memory? Okay, where is the combinational circuit? Plus 1, minus 1.
Yes.
Right?
That is the addressable memory.
Yeah. But one can argue that this feels like a stack.
But we
No, we
Also
can,
go
we
back.
can
Yes.
Up, down, and this.
Yeah, precisely. So we can increment the DPE, we can increment the data pointer without losing, we can decrement the data pointer without losing what was stored here.
Yes.
Right? So we decrement, sort of get the value, increment back again, and that value will still be there, right? Okay? So we have addressable memory in Brainfuck. Okay? And we have combinational circuits. Done. We are done. Because stacks we can always implement using addressable memory. Yeah.
But sir, how can we prove that this is enough?
I thought we had an intuitive discussion about that just now.
Like, even if we say this, like, we have till Turing machine, how do we know that there exists none other, like, method?
Good question.
We don't know what could be there.
Yeah. See this question mark here? Right? So this is meant to be a provocation to you. Okay? Try to prove me wrong. Come up with a logic that you cannot implement using these pieces of tools available to you.
So parallel computing is not possible with all.
Parallel computing, one can think about it as a bunch of Turing machines running in parallel. Isn't it? All right. Okay, so we figured out that Brainfuck is a Turing machine, right? Or do you feel that this is a bit in the abstract and abhi tak matlab, hit nahi kiya hai? It's not really settled in, is it? Okay, so to make sure that we actually get this really settled in, I'll give you a bunch of assignments. You need to you start with implementing add. Take two numbers. At DP position 0, DP position 1, you need to add. Remember, you don't have an add instruction. The only instructions that you have is plus and minus. So plus and minus along with condition and looping, can you implement add of any two numbers? Yes, no? At least at a high level we can imagine.
yes.
Right? Let's say we are adding 3 and 2, right? Okay? So we will loop 2 times and each time we can decrement 2 and the one that we are incrementing again and again is the 3. Possible? Right? So you guys will take an assignment of addition. Now the particularly aggressive kind of people can also implement multiplication. Multiplication we can do by repeated addition. Awesome. So we just now determined that there are 2 kinds of operations that were not there in the original VM ISA, but we now are able to compile a piece of code for that, right? The good part is the Brainfuck script is there on the repo, so you can test out your logic fairly easily. All right? Okay. Fair enough. So let's come back to what makes a VM. We discussed ISA, right? And through the Turing machine discussion, we also realized there needs to be a memory model. We need to have addressable memory. Okay? These are 2 core things without which you cannot have a VM. Make sense? If a VM has only ISA and no way of referencing addressable memory as in, you can always, addressability does not mean that it's randomly accessible. It can also mean increment, keep on reaching that, or decrement, keep on reaching it. In fact, Turing originally devised all of this as a tape, magnetic tape. So that is sequential access, right? You rotate it forward, rotate it backward until you reach the point that you want to. Yeah. Hard disk is also the same thing, okay? So ISA and memory model, 2 core components of a VM. Go ahead.
I was asking, like, from the previous slides, division is one of the operation that is not available on most of the codes and languages.
What do you mean division is available?
Like,
In Brainfuck it isn't available, but so is multiplication not available either.
It's like most manufacturers like don't support, like a few versions of assembly doesn't support division,
That is true.
and we have to write some different kind of code for that.
Or usually the compiler can, so long as there is basic array plus and minus available, you can simulate. Your compiler can produce code for multiplication, it can produce code for division. Yes. Okay, you also have better algorithms for it, but yes. Okay. So, and you should genuinely verify it, right? Because I could be lying. You have no way of validating what I said is true, except to actually do it and see it for yourself, right? So I strongly encourage you to actually do that. All right. So, question: when we were talking about languages versus VMs. Do languages have an ISA?
Yes.
Right? What is an ISA? It's a contract that helps you understand what do you want me to do.
Yes.
Right? In a way that I understand. Do languages have an ISA?
Yes.
For keyword, return, if, else, right? Definition of a variable, blah, blah, blah. All of those are ISA. That's a contract. Okay? Do languages have a memory model? Do languages have a memory model?
The language itself doesn't have one, but it can borrow it from the system. So,
Again, my question is memory model, not memory. I'm not asking for physical memory. The moment your language has a way to define a variable or an array or an object, it has a memory model.
yes.
Okay? So do you see how from a Turing perspective, a source code, a high level language is no different than the underlying ISA. The test is the same, addressable memory along with some basic compute. Okay? So technically you can implement a VM for Python source code directly, which is what your Python interpreter is. That's one way, like logically speaking, I'm not talking about practically how it's actually implemented. Do you understand what I mean to say? That's all about levels of complexity, levels of semantics. That is all that this is. The moment you start thinking about compute like that, it actually changes the way you think about languages. Okay? Suddenly assembly language doesn't sound scary anymore, it's just another language. Okay? So let's get to a particular aspect that is going to be crucial when we, when we think about VMs. When we think about, let's say there's an add function, takes in two parameters, 10 and 20. There's one way that you can implement registers. Do you guys remember from the earlier classes?
Yes.
Right? So, like every machine, or normally almost every machine will have some register, particularly the program counter. Program counter is the one that is stepping through instruction one by one, okay? And you'll have a bunch of registers, okay? Let's say R1, R2, R3. So, one way to implement this ISA is this notion that move 10 to R1, okay? So 10 got put into register 1, 20 got put into register 2, and then I call add R3 is equal to R1, R2, R1 plus R2. That is what essentially the last instruction means. This is called a register based machine. These terms we will be coming across. Isliye I'm sort of just giving you, this is a dump part of this session. Okay, this is a register based machine where the instructions have been implemented in a way that makes use of registers as scratchpad memory. Make sense?
In the previous slide, why there was a indentation below ISA?
Oh, no, there was no, that was just later on I'll be throwing in more terms in there. So it's just like, imagine these as pasteboard where you are just pasting a bunch of things, okay? All right, so you can also have, so I'll ignore this for the time being. So we have register-based machines, we have stack. So all of those of you who went through the JVM spec, you would have come across the word stack-based machine, right? So we looked at the register-based machine. These machines use the ISA to actually store value in registers, and that's how they calculate. Let's look at how a stack-based machine works. The instructions look something like this. There is a stack somewhere which we refer to as the operand stack, operand, O-P-E-R-A-N-D, okay? The way things work is, we push 10 to the stack, we push 20 to the stack, and then we call add. What add does is, pops 20, pops 10, adds them together, pushes it back. This is what is called as stack-based machines. Okay, clear? Register-based, stack-based? All right, good. One of the assignments for you is going to be thinking about as many differences as you can find between stack versus register-based machines. Okay. So, we have a third defining criteria of what makes a VM. We knew about the ISA and the memory model. We now have what is referred to as the machine model. Sometimes you'll also call this as the execution model. Okay? Because are the instructions executing by using the registers, or are they executing by pushing on the stack and then popping off the stack? Okay? So you'll have register-based machines or stack-based machines. Your physical machines, for each and every one of you, the ones that you're using right now, are register-based machines. Okay? Majority of the virtual machines tend to be stack-based machines. We'll come to that. One question is, what are we not currently talking about? I/O. We talked about compute. We didn't talk about how VMs interact with the external world. Right? Through the ISA and the Turing machine concept, and obviously coming from the memory model, we have the Turing machine. Right? This tells us, the machine model tells us the way that the is compute being done using registers or via the stack. Okay? Usually almost every machine will end up interacting with the external world. So some kind of I/O would be needed. We've not yet talked about it. And lastly, the concurrency. I think one of you were talking about concurrency. Okay? So these are some pieces that we'll figure out in a bit. But this is the lens with which we look at a VM. So any VM that I come across, the first question that I ask is, what is the ISA that it uses? What is the memory model of that VM? What is the machine model of that VM? And then sometimes I come to these two. Okay? So, ISA to ISA. This is what we normally see. ISA 1, this could be your JVM bytecode. This could be your underlying machine. Underlying machine's ISA. Okay? Your JVM is the one that is doing this conversion. Okay? It could be software emulated or hardware assisted. Okay? Somebody was talking about there would be scenarios where the bytecode could be directly translatable into something that is there in my underlying machine. In those cases, you can think about it as hardware assisted, because you can directly map that instruction into some other instruction of the underlying machine. We also sometimes have this, translation between the same ISA. For example, when you run a Linux machine on a Windows machine, or a Windows machine on a Linux machine, the ISA is the same, because both of them are executing your Intel or AMD machine language. Okay? But you still have translation going on because of some memory models and stuff, how the operating system does the processing. But I just wanted to highlight that often enough you'll also have translation going on between the same ISA. Okay?
So why they will both be on the same ISA? Let's say I am running a Windows subsystem on Linux.
Okay.
So it will be converting some code into a different ISA after the...
No, ISA is the same.
Why?
ISA is the same. ISA is the language that your processor understands. When you are running, for example, QEMU or any of these emulators or VMware or any of these things, what they are doing is they're doing what is essentially sandboxing. Okay, they are carving out a sandbox, which, remember, operating system always wants exclusive access to the hardware. Okay, one of the things that this lecture is not suitable for is how an operating system gives the impression of full CPU and memory access to each process, right? It multiplexes the processes. The operating system is running multiple processes at the same time, right? It does that by giving an impression that all of this memory is available to you and doing some memory management behind the scenes. It often uses hardware specific features to do that. Okay, virtual memory management is the word that you are looking for. Those things is why you actually need to run a virtual machine like VMware or QEMU or something like that. Okay, it's not the ISA that is the reason why you actually need to run it like that. It's the sandboxing, because Windows is assuming that you are giving me the full machine. Understood? Okay.
What is the VM of the VM which we use to run OS and the VM which we use to run Java is different, because in Java we don't use much IO, right?
That's actually one of the assignments. That when we get to the JVM slide, we'll talk about one of the assignments being how does Java talk to the external world.
A system VM and a program VM, they both are different.
They are different in some forms, but they conceptually remember that all of them end up talking about the same thing. Okay, so your system VM still has an ISA of your underlying processor. It has a memory model, which is flat memory available to me. Very early days of programming, it used to be segmented memory model that was available, but now it's a flat memory model. It has a machine model. Most of these processors use registers, so it's a register-based machine model, right? Exactly the same thing exists for your Java virtual machine. Java virtual machine uses the stack machine model. Its memory model we'll come to that, and it uses Java bytecode as the ISA. Conceptually, it's the same, but operating at different levels of hierarchy. Okay, it's just that. But conceptually, they are pretty much the same. In fact, in the early days of Java, there were a bunch of people who started creating chips, processors, that could execute bytecode natively. Okay, so yeah, food for thought.
Why call it system VM if it is an actual machine and not a virtual machine?
Everything is a machine. The only reason why we talk about that V part, the virtual part of it, is because we are emulating, simulating, or translating. That is the only reason. But all of them are pretty much exactly the same thing. Okay? Technically, you could build a processor that has the ISA of bytecode. Okay? You could build a processor that, a physical processor that has the ISA of bytecode, the JVM bytecode. And you could build a machine the way that you actually are using the machines. That is what I meant by in the early days, some of the people were doing that. Okay? Methods of running. We touch upon this beach mein. The simplest way is interpreted. It's also the slowest, naturally. You're picking one bytecode by one bytecode and executing, instruction by instruction is the line is the ASCII thing, right? Instruction by instruction, you are going in and executing those instructions, correct? And for every instruction, you figure out how to get it done in the native processor. That is what your Java is doing, okay? JIT is while the bytecode is running, I figure out some parts of it and convert those parts into the native code. If I can do the interpretation, I can also do the conversion, the compilation into the native code, correct? Naturally. It's just about the stage at which you're doing. Lastly, there is AOT, ahead of time. Okay? So, this, we'll talk about some of the VMs which do that. Let's get into the JVM. Bytecode. What do these instructions tell you about the machine model? Stack based or register based? Right? Why should JVM be designed for stack and not registers when majority of the processes are registers? Any thoughts?
Language might not have access to registers.
Okay, there's no guarantee that the underlying processor has registers. Okay, memory address. Any other thoughts?
A lot more instructions.
A lot more instructions. If you are using stack based, then you probably will have more instructions. Is that what you mean? But then that's a disadvantage. So why would you actually have?
No, we can manage more instructions.
We can manage more instructions. Okay. Yeah, there's some bit of truth to it, but there is an explanation that is sort of eluding you right now. You're not catching that yet. Any other thoughts?
Maybe someone just started and it became the trend.
There's truth to it. Okay, at some of the original or very early VMs that actually came up were actually essentially language-oriented VMs, and a lot of them used to be stacked, and simply because the previous guy had actually done stack, just like all of us. खुद सोचा नहीं, but पिछले वाले बंदे ने सब कुछ सोच समझ के किया होगा. Let me also use the same thing.
JVM does not have direct access to registers.
But your Java does, right? So if JVM exposes out registers, your Java command can still map the JVM registers into the underlying machine registers. So that's not an explanation. Well, let's say JVM declared 30 registers. What if the underlying machine has only 10?
What if it doesn't have any register?
What if it doesn't? Yeah, that is obviously there, yeah. Okay. The point is that doing that mapping becomes tricky. It's just a lot easier to, for some of the processes of this conversion if you are using stack-based approach. Compilation is actually easier in, from source code to this, because your compiler is not having to figure out which variable to allocate to which register. And what if I am running out of registers? That thing is called register pressure. Okay, compilation becomes actually much simpler. And at runtime, your VM, your Java command, still has the ability to compile. You remember that hardware optimization we were talking about? It might see that, okay, I'm seeing these series of this pattern of thing, load, add. When I'm doing the JIT compilation, I may actually convert it into a register access. That's the compilation I've done. Okay? At a bytecode to the underlying native ISA. Okay? Those possibilities exist. Stack-based machines just much simpler from a portability perspective. Okay? Let's look at how the JVM actually operates internally. We know that there can be multiple threads. What does the memory model of JVM look like? Heap memory, you guys are aware about it? Yes, no?
Yes, sir.
Okay. Perm gen space, aware about? Whenever a class gets loaded, its code is stored there. There's also a code cache for in some native compilations, JIT compile into native code. Those things are frequently used code. Those pieces are there. Okay. The heap memory is further divided into old gen space and young gen space, and young gen is further divided into this. You guys can read up about it on your own. The point is that the memory model is object based. It's not giving me linear memory. Like physically you can, in your physical machines, you can access this byte, that byte, etc. Right? Even if you have classes and all of those things, if you're writing C or C++ code, you can still access each byte separately. JVM's memory model does not allow that. It does not allow address pointers. Okay? You can only have references to objects. So the memory model. Okay? Each thread should have its own program counter naturally, because each thread is executing a series of instructions, right? For each function call, what each of these threads do is, for each functional call, there's a stack frame that gets pushed. Stack frame, let me call that function, another stack frame. Okay, it's, stack grows downwards is what we usually say. Okay, so there's a pre-existing stack frame. Let's say there was a function called done, another stack frame got pushed, another stack frame got pushed. Let's look at what is there in these stack frames. Okay, it's a local variable array. So you remember load 0, load 1, load 2.
Yes.
Those 0, 1, 2 are slots in here. Okay, so you say load 0, it means load the value was here, use that and push it into where? Operand stack. Remember, JVM is a stack based machine, which is why we have the operand stack. Make sense? And we have a bunch of references into the code of the class that was loaded. Okay?
There is no limitation on the amount of size the array can have.
Good question. What do you think should be the case?
It's hard to predict because we can make array inside our Java program. Then
Yes.
They are also primitive. So they will be stored in the stack.
When you create an array,
Yeah, we use new keywords, so it will assign memory, heap, and store a reference in the
yes,
stack.
right? So that is when you do a new array, the array is getting created here. And here in one of the slots, it gets put in the reference, right? But to your question, this array is going to be limited in size. Okay, you can always browse the OpenJDK source code to actually figure out what the size is. All right, and try writing a source code that has more number of variables in a function than that number. It should fail to compile. Make sense? Okay, so this is how the JVM actually operates. I load 0 means pick this, push into the operand stack. I load 1, picked this, pushed into the operand stack. Then I add and I return. Make sense? All right. By the way, .NET works very similarly. .NET, Microsoft .NET has very, very similar architecture. Okay. The assignment is, how does JVM interact with the external world? Somebody had, okay, so how does system IO println actually end up getting exhumed? One obvious hint is that the JVM provides for the implementation of some of these classes. Okay, but how exactly things get traced down to that is something that you guys need to explore. Okay. Last VM and then we are done, because I had more VMs, but I'm just going to give you WASM, WebAssembly, is a virtual machine designed for the web, as you can imagine. It is in the name. Okay. This is what a textual representation of the same thing looks like. We refer to this as what WASM text format. The same, this is the same thing can be expressed in a very, very binary sort of a form as well. But this is essentially think about this as the assembly equivalent of, remember we were talking about assembly language versus machine code, right? Pretty much two representations of the same thing. So this is the textual representation of that machine code of WASM, okay? You have add, you can see that, WASM is also a stack based machine, which means that it will have an operand stack, things get pushed, calculated, things get popped, calculated, pushed. Okay? Logic is pretty much the same. WASM, unlike Java had a heap memory and you could not address individual addresses. WASM actually gives a linear memory, like your physical RAM to your programs. That is what WASM actually gives to its modules. Okay? Because it is linear memory, so it has linear memory instructions, and a part of the linear memory is dedicated to the stack, which is where the pushing, popping, etc. happen. Okay? Can you compile C onto the JVM? Remember, JVM's memory model was memory model, not machine model. Memory model. There's a heap, a part of the memory area, but we could not randomly access any. There is no address inside that we get. Remember that new instruction that we saw? Right? The new instruction allocates a memory and populates the handle to that memory in one of those slots in the variable. That variable, local variable array that you guys remember, just puts in a handle to that area. It's not addressable memory. We cannot reach it randomly. This guy does. WASM allows us to do. That is its memory model. If JVM does not allow random access to the memory, is it possible to compile C on JVM? Remember, a Turing machine can calculate anything. JVM is a Turing machine, right? So technically you can run C, but it will be very interpreted in nature. That's the best you can do. Because you cannot access memory directly, and C's memory model is linear memory. If you guys may not know C, but C's memory model allows you to have pointers to any part of the memory. Okay? So C's memory model is different than the JVM's memory model, which is why JVM is restricted to very specific kind of languages. Whereas WASM, you can compile Rust on it, you can compile C on it, C++, JavaScript, even Java, right? So imagine Java itself is a program, right? This is the representation of actual machines, right? So you can actually compile Java onto this, all right? So WASM allows you to have different modules. Safety is a very important thing because it's designed for the web. So each module gets a different memory. That's one of the safety aspects of this. When think about WASM, there's something called WASI that you'll come across. WASM is just the VM. Remember that IO part? WASM was designed to essentially just be embeddable in the browser, but a bunch of people came up and said, it's great, it's awesome, all right? Just like Docker containers exist, you can actually have WASM containers. So WASM, a .wasm file actually becomes a distributable package. Just like we have Java to run class files, we'll have some WASM runner to run WASM files. But how do we do IO? In case of Java, there were external things that were exported out. What WASI does is, it allows you to inject certain functions. WASI injects specifically the POSIX. You guys know POSIX? So there's a bunch of standard APIs. Open, close, open file, close file, read socket, read network data, write network data, these sort of things. Okay, all the libraries are built on top of these APIs. Those APIs become available to the WASM piece. That's how IO happens in the WASM module. Okay, so I'm going to skip PTX. NVIDIA GPUs, remember? GPUs, actually, your NVIDIA compiler compiles to a VM called PTX. The reason why I included it is because its memory model is very different than the other memory models because it's designed to run on GPUs. It's, but we don't have time to go through that. So what happens is it gets compiled into PTX, and that runtime when your driver is actually sending code to GPU, it actually does that transpilation from the PTX bytecode, PTX ISA, into the actual chipset that is there on the GPU. Okay, we'll skip these. It's register based. That's the reason why I had included it. That not all VMs are guaranteed to be stack based. Okay. eBPF is another VM that is designed to run dynamic code directly inside the kernel. High performance, safety oriented, blah blah blah. I think we'll get to the summary. VMs. Do we have a better understanding? Yes, no? Okay. Basic structure, ISA, machine model. Machine model was stack or register. Okay. Memory model, IO and concurrency. Thank you.
The security you said.
Sorry?
Security that VMs provide.
the security piece is in the form of different VMs provide different kinds of security. For example, if you think about JVM, by virtue of the fact that it does not allow direct memory access, you can access memory only via the allocated object and its handles. There is no buffer overflow or these kinds of exploits that are possible on the JVM. Unless the JVM itself, unless the Java command itself has a bug, which sometimes there are, your Java code bug cannot be usually used to get into the, break into the host machine. Okay. Similarly, eBPF, because it's designed to run inside the kernel, its ISA is very limited. Its ISA is very limited. For example, there's a verifier that actually runs through that ISA to check that this piece of code is guaranteed to terminate because it's running inside the kernel. So we use eBPF to dynamically plug in a piece of code into the kernel from the user space. Kernel is a very high security zone, right? So not any code should be running. eBPF, because its ISA is so restricted, its safety can be verified. So that's another example of security. WASM's separation of linear of memory from one module to another is yet another example. But you need to design the VM for it. If your VM exposes out the memory, like khula maidan, then it would be, then you are opening it up for security issues. Any other questions, folks? All right. Sorry.
It is not much different than a programming language.
It is not much different than a programming. One of the takeaways that I wanted you guys to have is that theory of computation hierarchy. Remember that ISA and memory model, these concepts exist even at a programming language level. Okay? It's just about levels of semantics. Very high level semantics, intermediate level semantics, low level semantics, machine, actual physical machine levels. That's all. Make sense? All right. Thank you so much.